Find the fourth degree Maclaurin polynomial for f of x equals 1 over 1 minus x. So the Maclaurin is centered at 0. Let's write this as 1 minus x to the negative 1. And when we plug 0 in, that'll be 1 minus 0. That's 1 to the negative 1. That's 1. The first derivative, centered at 0, is negative 1 minus x to the negative 2, but then times negative 1, which makes it 1 minus x to the negative 2. Now when we plug 0 in here, we get 1 to the negative 2. That's also 1. The second derivative is equal to, let's take this one right here. We have negative 2 times 1 minus x to the negative 3, but then times negative 1. That's the chain rule. We get 2 times 1 minus x to the negative 3, and when we plug 0 in, we get 2. The third derivative is, let's take this one over here, negative 6 times 1 minus x to the negative 4, and then times negative 1. There's your chain rule. And that's equal to 6 times 1 minus x to the negative 4. And when we plug 0 in, we get 6. And then finally, the fourth derivative is equal to negative 24 times 1 minus x to the negative 5th, but then times negative 1. And that's going to be 24. Whoops, I wrote 25. Let's try that again. 24 times 1 minus x to the negative 5. And then when we plug 0 in, we're going to get 24. Well, that's really 0 factorial. That's 1 factorial, this value right here. We have 2 factorial, 3 factorial is 6, and 4 factorial is 24. Now when we write the polynomial of fourth degree to estimate this function, we get 1 plus x plus, and then we'll get 2 factorial x squared over 2 factorial, because 2 is the coefficient, which is the same as 2 factorial. And then plus 3 factorial x to the third over 3 factorial, plus 4 factorial x to the fourth over 4 factorial, and that pattern would keep going. So the fourth degree Maclaurin polynomial for this function is 1 plus x squared plus x to the third plus x to the fourth. And we could keep going with this, but that's the fourth degree. This is called the power series. The factorials all cancel out, and you're just left with the powers of x. This is also a geometric series. Where a sub 1, the first term is 1, and r is x. We're multiplying by x every time. We can write this as, or in summation notation, we have n equals 0 to infinity of a sub 1 times the r raised to the nth power. When we have a geometric series, the sum is equal to a sub 1 over 1 minus r. And in this case, a sub 1 is 1, and the r is x. So look how we kind of end with what we began with. This is the function that represents this series. And we kind of already knew that. We were given that. So the sum is the same as the function that represents the series. Now this is going to converge as long as the absolute value of x, or r, is less than 1. So as long as x is between negative 1 and 1, this is going to converge. Negative 1 to 1 is called the interval of convergence. So this is the interval, that's an r, interval of convergence. Now there's another term that you're going to need to know. If the interval of convergence is negative 1 to 1, then we can plot this interval. We can go from negative 1 to 1, and then half that distance is the radius of convergence. So the radius of convergence is equal to 1 in this case. Let's talk about what it actually means to have an interval of convergence. Let's go to the calculator. And in y equals, in y1, I have the function 1 over 1 minus x. And then in y2, I've put the Maclaurin polynomial, but only the second degree. And let's graph the function and then graph its approximation. And here's the window. We're graphing x from -2 to 2, and y is going from -2 to 8. So here comes the skinny line. This is the actual function, and this is the approximation. And you can see that the approximation is good from -1, and then it starts to fail before we get to 1. It starts to become bad. And actually, on the first function, x cannot be 1 because that would make the denominator 0. Let's go back to y equals. Let's turn off the second function. And we'll turn on the one that I've taken all the way out to the 9th degree, to the 9th power. When we graph this, we get the original function again. And then very slowly, here comes y3. And notice it's good from -1. And then it's really good, really good, really good. But then once it gets towards 1, once it gets close to 1, it starts to fail. So no matter how many terms you have, this approximation is only going to be good from -1 to 1. And that's why the interval of convergence is from -1 to 1. Power series. F of x is the sum from 0 to infinity of a sub n x sub n. That's a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x to the third. So you have the powers of x. This is what you get when it's centered at 0. Then when you center the power series at something other than 0, then the x's become x minus whatever you're centering it at. So this would be centered at c. Find the interval of convergence and the function of x represented by the geometric series. So we want interval convergence and then the function representation. So this is a geometric series where a sub 1 is equal to 3. If you plug 0 in for n, this whole thing goes to 1. And then r is equal to x minus 1 over 2. Now, the interval of convergence will happen where the absolute value of x minus 1 over 2 is less than 1. So by definition of absolute value, we can write -1 is less than x minus 1 over 2 is less than 1. Let's multiply everybody by 2. We get -2 is less than x minus 1 is less than 2. And then when we add 1, we get -1 is less than x is less than 3. So the interval of convergence is from -1 to 3. So there's the interval of convergence. Now we want the function that represents this geometric series. And that comes from the sum. So the sum is going to be the function. And the sum is a sub 1, which is 3, over 1 minus r, which is x minus 1 over 2. Now we can't leave that as a complex fraction. So let's multiply everybody by 2. That gives us 6 over 2 minus x minus 1. And we are minusing this whole thing, so we need parentheses around this. So we have 6 over 2 minus -1, that's 3 minus x.